Every single device you interact with today, your smartphone, your laptop, your smartwatch, even the dashboard in your car, relies on the exact same piece of hardware, a tiny silicon chip that makes billions of decisions every second. But if you actually stop to think about it, how does a microscopic piece of silicon do all of that? Does it understand English? Does it know mathematics, or physics, or color theory? Processors are oblivious to human concepts. This diagram shows a complex file, like a photo or a text message, being stripped down into a simple stream of ones and zeros. Processors only recognize two basic electrical states, on and off. This raises a question. If a chip only speaks in ones and zeros, how can it render a hyper-realistic, multicolored video game environment? Everything a computer does is an illusion. It is the result of billions of microscopic switches following blind instructions in perfect synchronization. A processor is a collection of specialized departments, each designed to handle one specific task. This schematic maps out the internal architecture. Right here is the control unit. It acts as a traffic director, receiving incoming binary instructions and routing them down distinct pathways to their correct destinations. Once routed, those instructions often land in the ALU, or arithmetic logic unit. This is where mathematical calculations and logical comparisons are executed. It takes binary inputs, performs the math, and sends out a single definitive answer. To perform that math instantly, the ALU needs immediate access to data. These tiny memory lockers built directly next to it are called registers. They hold the exact numbers the processor needs at this very second. For information it might need in the next few seconds, the processor relies on cache. This outer ring of memory acts like a bookshelf next to a desk, keeping frequently used data close so the processor never has to wait. These specialized components only matter because of the precise, synchronized rhythm at which they operate together. Every calculation rests on a single repeating loop, the fetch, decode, and execute cycle. During the fetch phase, the processor reaches into the memory bank and grabs the next instruction in the queue. During the decode phase, the processor figures out what the binary actually means, translating it into a specific task. Finally, in the execute phase, the processor performs the math or moves the data, finishes the job, and the loop immediately resets. Try to guess how many times that cycle happens in the time it takes you to blink. The answer is millions. We measure this volume using clock speed. A processor advertised at 4 GHz is completing 4 billion of those cycles every single second. Modern chips also use multi-core architecture to gain speed. They divide the workload among multiple independent cores working in parallel. The power of a CPU lies in its ability to perform these simple tasks with incomprehensible speed and parallel scaling. Flipping billions of microscopic electrical switches every second has a physical cost. The electrical friction of all that activity generates intense heat. For engineers, this creates a major physical bottleneck. If the cooling system fails, a processor will initiate thermal throttling. It will intentionally slow its own clock speed to prevent the silicon from literally melting. When you zoom out from the microscopic pathways and look at the motherboard, everything you see is built to support this single microengine. Our digital world is built on this microscopic engineering. Blind instructions executing billions of times a second create every experience on your screen. Tell me in the comments, which processor powers your device? And if you learned something new, hit like and subscribe. Thanks for watching.